name of Almighty God, I'm Martha Sankoshi, and today I want to talk about Introduction to Battery Design Module in Quantum Multiphysics Simulation Software. The battery design module offers a wide range of functionality for modeling and simulation of batteries, from the fundamental processes in the electrodes and electrolytes of batteries to cell temperature and current distribution in battery packs. These simulations may involve the transport of charged and neutral species, current conduction, fluid flow, heat transfer, and electrochemical reactions in porous electrodes. You can use this module to investigate the performance of batteries at different operating conditions and for different electrode configurations, separator, current collectors and feeders, materials and chemistry. The description of the involved process and phenomena may be defined in a fairly detailed manner, allowing you to apply different hypotheses to gain an understanding of the investigated systems. With these detailed models, you can study the influence of different electrode materials, pore distribution, electrolyte composition, and other fundamental parameters on various aspects such as battery performance as well as the capacity and power fade. The module also allows for more lumped black box modeling approach where detail and knowledge of the battery chemistry is not required. Such lumped models can be used for investigating cell-to-cell dynamics, impacts, thermal management, as well as battery dynamics in electrical circuit simulations. The smart set of parameters used in lumped models are well suited for fitting to large cycle experimental data. Parameter estimation tools implemented with optimization solvers are also included in the battery design module. You can couple the battery models to other physics such as heat transfer, fluid flow, structural mechanics, and chemical species transfer in order to study phenomena like aging, heat dissipation effects, and stress-strain relationships. You see, we have electrochemistry, and the sub-branch is primary and secondary current distribution, and primary current distribution, secondary current distribution, tertiary current distribution, named spelling as a physical module, tertiary electroneutrality, tertiary water-based with electroneutrality, tertiary supporting electrolyte, tertiary Poisson. The next is batteries, lithium ion battery, the form geometry, lithium ion battery, single ion conductor battery with binary electrolyte, lead acid battery, and lumped battery, two electrodes, and battery equivalent circuit battery pack. And also we have a closed secondary current distribution, closed tertiary, coded tertiary current distribution near Spelunk, coded current distribution boundary elements, and coded current distribution on edge boundary elements. Figure 1 illustrates the three-dimensional physics interfaces for the battery design module as shown in the model wizard with the electrochemistry branch fully expanded. The figure above shows the available physics interfaces in the battery design module under the electrochemistry branch. These electrochemistry interfaces are based on the conservation of current, charge, chemical species, and energy. The battery interfaces form the basis for battery cell and pack modeling. The chemical species transport, the fluid flow, and heat transfer interfaces are extended with functionality for battery modeling. For instance, features for handling porous media. The different physics interfaces are further discussed below. The first one is battery modeling. The battery modeling design module has a number of physics interfaces to model batteries. Choice of physics interface depends on the overall purpose of the model. The first step is detailed cell models. When studying the cell chemistry, aging, or high charge discharge rates, one typically resolves the different layers of the battery using space-dependent models on a micrometer scale, whereas coarser models for computing heat sources or predicting the voltage behavior for low or moderate charge discharge rates may use a more lumped modeling approach. Space-dependent battery models often model unit cells that consist of the current collectors and current feeders, porous or solid metal electrodes, the electrolytes that separates the anode and cathode, the To exemplify, the following describes some of the charge and discharge processes in a rechargeable battery. During discharge, chemical energy is transferred to electric energy in the charge transfer reactions at the anode and the cathode. The conversion of chemical to electric energy may involve electrochemical reactions, transport of electric current, transport of ions and neutral species in electrolyte, mass transport in the electrode particles, fluid flow, and release of heat in irreversible losses. Figure 2 shows a schematic picture of a typical discharge processes. Figure 2 illustrates the direction of current and charge transfer current during discharge in a battery with porous electrodes. You see that we have a negative electrode as an anode and positive electrode as a cathode, and you see that the direction from the negative to the positive, you see that the electron are transferring from the negative electrode to the positive electrode, and the current in a negative electrode is by the blue line and blue arrow. The current in an electrode is with green arrow, and current in positive electrode are in a purple arrow. Anodic charge transfer reaction are such as the curve arrow to the downside, and cathodic charge transfer are which is green arrow up to the curve to the upside. The current enters the cell from the current feeder at the negative electrode, and anodic charge transfer reaction occurs at the interface between the electrode material and electrolyte contained in porous electrode, also called the pore electrolyte. From the pore electrolyte, the current is conducted by the transport of ions through the electrolyte that separates the positive and negative electrode via a separator or reservoir to the pore electrolyte in the positive electrode. At the interface between the pore electrolyte and the surface of the particles in the positive porous electrode, a cathodic charge transfer reaction transfers the ionic electrolyte current to current conducted by electrons in the positive electrode. The current then leaves the cell to the current collector. The conduction of current and electrochemical charge transfer reactions will release heat due to ohmic losses, activation losses, and other irreversible processes. Looking closer at the charge transfer reactions on both electrode interfaces, Figure 3 describes the polarization of the electrodes during discharge. The graph plots the charge transfer current density I local as a function of electrode potential E. Figure 3 shows electrode polarization during discharge. The figure is same as inset of figure 2. The negative electrode is polarized anodically during discharge of positive current as indicated by the arrow in figure 3. The potential of the negative electrode subsequently increases. The charge transfer reaction involves oxidation of either the electrode material or a reactant in the electrolyte. The shape of the polarization curve is governed by the electrode kinetics for the specific materials. The resulting local current density is denoted as I local I star. Similarly, the potential at the positive electrode decreases through cathodic polarization during the cathodic charge transfer reaction. The electrode material or reactants are reduced, which the observed current density being denoted. Figure 3 also shows that the potential difference between the electrodes, here denoted ESL, decreases during discharge compared to open cell voltage, here denoted EA octave. In the description, losses in ESL through ohmic resistance and mass transfer electrolyte and electrode particles were neglected. Both effects may occur in many batteries and can be included in a model with the battery design module functionalities. Figure 4 shows the reverse processes in the battery during charge electric energy in transfer to chemical energy stored in the battery. Figure 4 shows during charge the positive electrode acts as the anode while the negative one acts as the cathode. The cell voltage increases at a given current compared to the open cell voltage. Note that direction of the current is reversed here. The current enters the cell at the positive electrode here during charge and oxidation of the reactants take place through an anodic charge transfer reaction. The positive electrode is polarized anodically with a positive current and the electrode potential increases. The current is then conducted through the positive electrode, pore electrolyte through the electrolyte in the separator or reservoir to the pore electrode in the negative electrode. In the negative electrode, a reduction takes place through the cathodic charge transfer reaction. The negative electrode is polarized cathodically and the electrode potential decreases. Figure 5 depicts the polarization of the electrode during charge. Figure 5 shows electrode polarization during charge. During charge, the cell voltage ESL is higher than the open circuit voltage OCV. Again, losses through ohmic resistance and mass transfer in electrolyte and electrode particles were neglected. The output further increases ESL, the battery process, and the phenomena described. The figures above can all be investigated using the battery design module. The physics interfaces included in the module allow you to investigate the influence on battery performance and thermal management parameters such as the choice of materials and chemistry, dimensions and geometry of the current collector and feeders, dimension and geometry of the electrodes, size of the particles that the porous electrodes are made of, porosity and specific surface area of the porous electrode, configuration of the battery components, the kinetics of interfacial and bulk reactions, potential or applied current dependent load cycles, aging of electrochemical cells. Now I want to go through the lumped model. When modeling larger systems such as battery packs, it can be partial and practical to neglect detailed descriptions of the phenomena occurring between the individual batteries. Many details about the battery cell may not be known to the modeler, and computational cost, more memory, and computational time move may favor less complex models. For these cases, one often replaces the detailed cell model by simpler zero-dimensional cell elements, forming an equivalent circuit, lumped battery, or single particle model. For instance, instead of detailed mass and charge balance of charge carrying ions in the electrolyte phase along the length of the negative electrode separated and the positive electrode, all voltage contributions from these phenomena are lumped into a single resistor. In a battery pack model, a number of these zero-dimensional models for each battery cell are then combined to define the cell-to-cell current distribution of the pack. Thank you so much for watching my tutorial video until then. Today is 24th of May 2026. The time is 7:20 p.m. Also, you can download the proper and appropriate and related console file from my github.com/master script.